Hi everyone, welcome to part 1 of our video lecture on section 3.3 dealing with the derivatives of polynomials and exponential functions. So in this set of videos, we're going to learn how to differentiate constant functions, power functions, polynomials, and exponential functions without the need to use the limit definition of the derivative. These rules that we're going to be learning are what I like to call the shortcut rules. So let's go ahead and get started with one of the easier derivatives, the derivatives for constant functions. All right, so if we're given a constant function, let's say f of x is equals to c. So if we're given that function, how does that graph look like? It's going to be a line. So if we have a line, what is the slope for that line? Well, let's see. Well, if I were to graph it here, you may remember that if you're trying to graph a constant function, well, it's just a line that, well, is horizontal going through the y-coordinate of c. So here's my line y equals to c, or f of x is equals to c. And if I wanted to figure out the slope, well, because it's a flat line, the slope is 0. Well, if the derivative is the slope of the tangent line, well, the tangent line here to a line, well, it's just the line itself. So that means then that the derivative for a constant function is also going to be 0. So for this one here, I'll write down, hey, f prime at c, it's also equal to 0. And there we go. All right, so what we just shown here is that the derivative of a constant function given by f of x equals to c is given by the derivative with respect to x of a constant is equals to 0. So now anytime that I want you to find a derivative, and if I'm giving you just a constant, the number, you know that the derivative is equal to 0. So let me give you guys a couple of examples here. So let's say that I gave you f of x equals to 10. All right, that function is a constant. So just you know here that the derivative for f is just 0. Or another way of saying it here, f prime is equal to 0. Or if I gave you the function y equals to 150, well, y prime is just going to be 0 again, because it's a constant. Okay, so I made the argument for the derivative of a constant being 0 through the use of the graphs here, but would the limit definition still apply here? Well, let's take a look. Let's go ahead and use the limit definition given the function f of x is equals to c. All right, so the limit definition was the limit as h goes to 0 for f of x plus h minus f of x all over h. All right, so when you're doing the limit definition, remember our input was the x plus h, but the thing about inputting an x plus h into a constant function is not going to matter. It's still going to be the same function. It's still going to be the same constant. So all of this one here is still going to be equals to a c minus, all right, now the function, the original function here was a c. In fact, I'm going to go ahead and put them in blue here. All right, so this one is also a c. Okay, so what do we have then on the numerator? On the numerator, we're going to get c minus c, which is going to become a 0. So what we're really working with is then the limit as h approaches 0 for 0 over h. But right now here, guys, we have 0 in the numerator. That's just a constant. And remember, when we're evaluating limits, we need to simplify first before evaluating the limits. So right now, well, if 0 is in the numerator, well, 0 divided by anything is 0. It doesn't matter if the h is approaching 0, because again, the h is approaching 0, so it could be a 0.5, a 0.1, a 0.01. But again, because it's 0 divided by these numbers, it doesn't matter. It's still giving us a 0. Now, if the operations here seem a little bit weird, let me give you another example here with a number. Let's say that we had the function f of x is, let's say, 7. And I want you guys to evaluate what would be f of, I don't know, 5. Well, if the function is just a constant, f of 5 is still 7. Now, if I made it into 5, or f of 5 plus h, let's say, well, it doesn't matter. My function output is always 7. So that's why I got a c minus c on the top. With this new function, we would have basically gotten a 7 minus 7 over h, and the limit here, and we still would have gotten here a 0. So there we go. Now, I want you guys to remember anytime that I'm giving you a constant, and if you want to find the derivative of constant is just 0. Now, before we keep on looking at other derivative formulas, you're going to see me use this ddx quite a bit. Now remember, when we talked about this ddx here, this was an operator that was telling you to take the derivative. More specifically, this one here was telling us to take the derivative with respect to x. Okay, now I want to give you another formula that's very nice and very common actually as well. And this one here is simply the derivative with respect to x of x. So if we're taking the derivative with respect to x of x, the answer is just 1. Now I'm going to go ahead and use two approaches, the graphical approach here and the limit definition. So let's go ahead and begin here with the graphical approach. So here we have the function f of x is equals to x, or just y equals to x. If I ask you, okay, well, what seems to be the slope of this line? Well, then you might remember your slope-intercept formula, y equals to mx plus b, and you get to see here that, okay, this one here has a slope of 1. All right, so if our slope is 1, and again, we know that the derivative is the slope of the tangent line, but a tangent line with a line was just itself, so we get to see here that if the function is x, then its derivative is just going to be 1. All right, now this one here was the graphical approach. Well, what about the limit definition for the derivative? Okay, so we're going to get the limit as h approaches 0 for f of x plus h minus f of x all over h is going to be equals to, well, now let's see. If we're now inputting the x plus h into our function, we're going to get the limit as h approaches 0 for x plus h minus x all over h. And we get to see here that, okay, well, the numerator, you can cancel the x's. Then you're just left with the limit as h approaches 0 for h over h. And again here, simplifying first, h over h is just a 1. So really we'd just be left with the limit as h approaches 0 for 1, which is just 1. And there we go. Different ways of showing that the derivative with respect to x of x is just equals to 1. Okay, excellent. Now let's take a look at another problem here. What if I want you to find the derivative for f of x equals to x squared? All right, now this one here, I'm not going to use a graphical approach, but I will go ahead and use the limit definition for the derivative. So we're going to get here then f prime of x is equals to the limit as h approaches 0 for f of x plus h minus f of x all over h. And since our function is x squared, we're going to go ahead and give it the input of x plus h. So we'll get here the limit as h approaches 0 for x plus h squared minus x squared all over h, which is going to simplify to the limit as h approaches 0 for x squared plus 2hx plus h squared minus x squared. And I'm going to go ahead and do a literal simplification here. We have an x squared minus an x squared, that's going to give us 0. And now, since we are dividing by h, and I do have an h here for the 2hx, and the h squared has 2 of them, I'm going to cancel. So we're going to get the limit as h approaches 0 for 2x plus h, and as h goes to 0, then we're just left with our derivative function being 2x. All right, so we just saw right now that if we were starting off with the function x squared, the derivative was 2x. Notice here the power was 2. It was a number that was in front of the x. Maybe there's a pattern to it. Or who knows, maybe it was just a coincidence. Let's go ahead and take a look at another example where we're still dealing with a power function, but this time around, we're keeping things general. What if we wanted to figure out the derivative for the function f of x equals to x to the n, where the n here is just any power? Well, if we went ahead and used the limit definition of the derivative, then we would have been left with the following formula. The limit as h approaches 0 for x plus h raised to the n power minus x to the n all over h. Now, because the n could be any power, this particular problem could get really messy, because what if I wanted you guys to raise the x to the, I don't know, let's say the 8th power? Well, then I would have the x plus h raised to the 8th power, and I don't want to multiply the x plus h by itself 8 times. It'd be too long, too grueling. All right, so instead, I'm going to go ahead and reference the binomial theorem to expand the x plus h to the n. You don't remember the binomial theorem or you haven't seen it, that's okay. We're just going to use it for this formula. So the binomial theorem will tell us that if we have the binomial x plus h raised to the n, then this is going to expand into x to the n plus n times x to the n minus 1 times h plus n times n minus 1 over 2 times x to the n minus 2 times h squared. And we'll continue on with this pattern up until the last two terms, n times x times h to the n minus 1 plus h to the n. And this is what I'm going to be using here. All right, so going back to the limit definition of the derivative, we're going to get the limit as h approaches 0 for x plus h to the n, which we know that it can be expanded to all of this. So let's see, I'm going to go ahead and copy it down. There we go. This is the x plus h to the n minus x to the n. And don't forget, it is all over an h. Okay, now let's do a little bit of simplification. So I see an x plus n, and then I'm subtracting an x to the n. And now, just as we did in the previous example with the x squared, I'm going to go ahead and divide by an h. So dividing by an h here, this is gone. This one here is losing 1h. This one here is losing 1h. So if it was an n minus 1, now it's going to be an n minus 2. This one here will lose 1h. And let's see, after all of this simplification, what are we left with? Well, we'd be left with the limit as h approaches 0 for all of this. However, there's some very good news right here. I have a couple of terms that have an h, and only one term that does not have an h. Now, why is that important? Well, since you're taking the limit as h goes to 0, there's an h here as it goes to 0. All of this is going to vanish, goes to 0 here. All the in-between terms are also containing an h, so they're going to go to 0. The last two terms here, again, they have an h, so they're going to go to 0. And we're really just left with one term. It seems like the derivative of the function x to the n is just n times x to the n minus 1. So there was actually a pattern. So going back to this one here, where I gave you the function was x squared, if we remember the pattern here that f prime of x is just n times x to the n minus 1, if the function was f of x equals to x squared, then our n was 2, so the derivative would have been 2 times x to the 2 minus 1, which is just equals to 2x, and that's exactly what we got here. So now, we don't really need to go ahead and use the limit definition every time that we have a power function, or the derivative of a variable raised to a power. We can just go ahead and reference this result. And that's what we're going to have right over here. This is what I definitely want you to remember. This one here is known as the power rule for derivatives. So if n is any real number, then the derivative with respect to x of x to the n is just n times x to the n minus 1. And now we don't have to use a limit definition every time. Excellent. So now let's go ahead and get to practice using our power rule. So let's see, let's go ahead and take a look at, well, I guess I'll take a look at all of them. So it's on your notes or the video lectures here. All right, so let's take a look. All right, so let's go ahead and differentiate the following functions. Beginning with the first function, y equals to x to the 8th. All right, so we're going to differentiate. So it means that we got to take the derivative. So I'll go ahead and say, okay, well, I'm taking the derivative with respect to x for y, which is given by the function here x to the 8. So what I'm really doing then is finding the derivative with respect to x of x to the 8. And this is where the power rule is going to come into play. Remember, when you're taking the derivative with respect to x of x raised to a power, all you got to do here is bring the power down and subtract 1 from the power of x. Okay, so let's take a look here at our function here. The derivative of y with respect to x is just going to be here a y prime is equals to, all right, so we're going to bring down the power. So we're going to have an 8 times x, and then take away 1 from the power. So now we're going to get here an 8 minus 1, which is just going to give us here a 7. Okay, so there we go. If the function was x to the 8th, the derivative was simply 8x to the 7th. Okay, see how quickly it is, guys? Very nice, very nice. Now, what about the next one, though? The next one, now we have f of x is equals to 1 over x to the 6th. Now, can we use the power rule? Well, Again, remember the power rule was telling you if you have an x raised to the n. Right now, technically speaking, we do not have an x raised to the n. What we actually have in this problem here is a 1 over x to the n. Not quite the same thing. Okay, so does that mean that we cannot use the power rule? Not at all. It just means that we have to modify the problem a little bit. And this is where the rules of exponents come into play. You might remember here that, in fact, let me put it as a side note, that whenever we're given an x raised to a negative power, we can always turn the power positive by bringing the x down, and that's going to change the sign of the power. Essentially, you're taking the reciprocal here. All right, so how does it help us with our problem? Well, for our problem, if we have 1 over x to the 6th, we can go ahead and reinterpret this one here as being x to the negative 6. Now we can use the power rule. Okay, so we're going to go ahead and take the derivative. Then we're going to get the derivative of f of x with respect to x is equals to the derivative with respect to x of x to the negative 6. And using the power rule, we bring down the power. So we're going to have here a negative 6 times x, subtract 1 from the power. So negative 6 minus 1 is going to give us here a negative 7. So there we go. The derivative of 1 over x to the 6th is equals to negative 6 times x to the negative 7, which of course you can go ahead and rewrite as, let's see here, f prime of x, the derivative, is equals to a negative 6 over, because now I'm going to go ahead and bring the power down, x to the 7th. And there we go. Now we got our derivative function. Now I like this problem here because it's showing us that, hey, sometimes we might have a problem expressed in a way that it might seem like we don't have formulas, but that's where the algebraic manipulation can come to the rescue. All right, so let's take a look at another problem here, which I think is another good one as well. All right, so the third one here is giving us a function y is equals to the cube root of x. Now, once more, we have a radical, so it doesn't seem like the power rule applies. However, I want you guys to remember the following. If we have the nth root of x to the m, that is the exact same thing as x to the m over n power. So remember, roots are just rational exponents. Okay, so first thing to do for this problem then is to go ahead and rewrite it. We're going to get that y is equals to x raised to the 1/3 power. Now I have x raised to a power, and I can use the power rule. So differentiating, we're going to get the derivative of y with respect to x is equals to the derivative with respect to x of x to the 1/3, which gives us, again, using the power rule, bring the power down. So we're going to get here a 1/3 times x raised to the, and now this is where we have to be careful with fractions. Remember, we are subtracting 1 from the power. So what is 1/3 minus 1? I'll do it here. 1/3 minus 1. Put it over 1 here, and that's going to be equals to, LCD is 3, so we're going to multiply top and bottom on the second fraction by 3. So now we have a 1 minus 3, which is a negative 2/3. So then the power of x is a negative 2/3. All right, now this is the final answer, but if you want to go ahead and rewrite it with positive exponents, then we're going to get here dy dx is going to be equals to 1/3. Now we bring down the power, and that's going to be x to the negative 2/3, but since we brought it down, it's now a positive 2/3. Now, the last and final thing that you can do, although it is completely optional, you can go ahead and rewrite it with radicals again. So our derivative function for the cube root of x is also equals to 1 over 3 times the cube root of x squared. There we go. All these are the same answers. So whether you want to give me your final answer as 1/3 times x to the negative 2/3, or 1 over 3 times x to the 2/3, or 1 over 3 times the cube root of x squared, it's all the same. That's perfectly fine. Now going back to the previous problem, if you leave your answer like this, or like this, again, I have no problem with it. Although my open math might be looking specifically for powers that are positives. Okay, now, with that said, let's go ahead and take a look at the last 3 examples, but, well, let's go ahead and take a look at the last 2, because I want you to try the last one on your own. Okay, so let's take a look at the g of x function. Now this g of x function, we have e to the 8th. Now this one, I do want you guys to try it here. So let's go ahead and pause the video and see what you get for the derivative. Welcome back. So I want to go over one of the most common answers that I see for this derivative. So oftentimes I encounter the answer, the derivative of g is 8 times e to the 7th. Now unfortunately this is not quite correct, but if you got this answer, it's pretty good because it shows me that you are remembering the power rule, which tells you to bring down the power and then subtract 1 from the power. That's correct. That is what the power rule would be telling you. However, we have to be careful. Do we need to use the power rule? Well, take a look at the e to the 8. The e to the 8, is it a variable or a constant? Well, if you go ahead and graph the e to the 8 on your calculator, you'll see that you are getting just, well, a horizontal line, because the e to the 8th is a constant function. Because again, if I go to the calculator and say, okay, well, what's e to the 8th? It's going to be a big number, but it is just a number. It's close to 3,000. So if I rephrase this problem and ask you, hey, what is the derivative of 3,000? Or in this case, what is the derivative of 2,980.95? Well, that's a constant. And we just discussed here that anytime that we're given a constant, the derivative is just 0. So you gotta be careful here, guys. If you're gonna be using the power rule, make sure that the power rule is actually necessary. In this particular scenario, e to the 8th was a constant, and the derivative of constant is 0. Okay, so let's take a look at one more problem here, where we have the function f of x is equals to x to the pi. Now, is this one a constant? No, we have x raised to the pi power. Okay, well, if we go ahead and apply the power rule, then we're going to get, and for this one, guys, I'm not going to go ahead and write that ddx of f. I'm just going to go straight to the derivative notation here. But it's true, we are taking the derivative with respect to x. But I'll omit it here, or skip that step, and I'll just write here f prime of x is equals to the derivative with respect to x of x to the pi, which is going to be equals to, all right, now we use the power rule, bring down the pi, times x raised to the pi minus 1. And there we go. You found the derivative function for x to the pi. Now, before we end the recording, I want to make a couple of comments here. In the first couple of examples that we were doing, I was emphasizing that I was taking the derivative with respect to x of the left-hand side. And that is true. We are taking the derivative of both the left and the right-hand side. But notice here that in this last example, I just started with the function f, and I went immediately to the f prime of x. We don't always need to include the fact that we're taking the derivative with respect to x. Once we include the prime symbol, we're already implying that. I did include it on the right-hand side though, just to get you guys to feel more comfortable with the notation. You're taking the derivative with respect to x. But the truth is, as you guys start to work on more examples, feel better, get more proficient, you don't always need to include the ddx. You can just go from the original function and then give me the derivative. You don't need to write the ddx every single time. I will keep on doing it for this particular video, but now once we move on to the following sections, I will not be writing this all the time. Alrighty, now with that said, the video here is getting a little bit longer, so we're gonna stop it here shortly, but we are missing one problem here, problem 6, where we have y equals to 1 over the cube root of x squared. For this one here, guys, I want you to try, what is this derivative? So I want you guys to try it and submit it to Canvas. Alright, now, with that said, this is the end of part 1 for our video lecture on section 3.3. And on part 2, we're going to take a look at more formulas here. Alright, see you there.